So, good morning.
Good morning.
I hope you can see my document.
Yes, you can.
So, okay, so we stopped yesterday when we were looking at the distortionless line, and I said that distortionless line is not lossless. It's still lossy, but the losses are such that that ratio there, that is R prime by L prime, is equal to G prime by C prime. And the reason why we say it's distortionless is because both the characteristic impedance and the phase propagation constant are the same as in the lossless case. Now, what I want you to do as an exercise for the weekend is to get the value that is the gamma as written there, that not with the distortionless line, of course, but what I want to give you the task is the following. We have gamma expressed in that form, and the characteristic impedance expressed in that form there. So what I want you to do, we did a binomial expansion, and we retained only the first two terms, or the first two linear terms of the expansions for the two expressions. Now I want you to do this. You expand that binomial expansion, but retain the first three terms. That is, you'll include also the power of 2. Because many times, the reason why we were able to retain only two terms is because we said that R prime was much smaller than omega L prime, and G prime was much smaller than omega C prime. Sometimes some of these assumptions do not apply for certain transmission lines, and therefore you need to approximate the expressions with a few more terms. So this is an exercise to just show you what would happen, and therefore I want you guys to expand that and retain the first three terms of each expression, and then get approximate expressions for the attenuation constant, the phase propagation constant beta, as well as the characteristic impedance. And you show that this will now become functions of frequency, and when they become nonlinear functions of frequency, then we'll see that a lossy line is always going to be dispersive. Because if you recall from last semester, we defined a dispersive line as one in which the different phase components, the frequency components in a signal travel at different phase velocities, and therefore they start separating. And the example we gave for such an occasion that you can see in reality is the formation of the rainbow when the sun shines, when we have a light rain or some kind of moisture in the atmosphere. You'll see the colors of the line of the sunlight separating themselves into the distinct rainbow colors that we are so familiar with from primary school. So after you do that, so we can continue now, and I'll give you another example, and this is the following. That is, in an experiment, it's found that the attenuation on a 50 ohm distortionless line is 0.01 dB per meter, and the line has a capacitance of 0.1 nanofarads per meter, and therefore we are required to determine the resistance, the inductance, and the conductance per unit length of the line, and we find the velocity of the wave propagation. Usually this would refer to the phase velocity rather than the group velocity, and determine the percentage to which the amplitude of the voltage traveling wave decreases to in 1 kilometer as well as in 5 kilometers. Now, all the information you need has been provided. All you need to follow is the following. Distortionless line. When you are told about the distortionless line, therefore you already click in your head that all we are saying is that R prime by L prime is equal to G prime by C prime. We've been given a value for the capacitance per unit length. We don't have a value for the inductance per unit length, the resistance per unit length. But we also know that alpha is going to be given by a half R prime divided by Z naught. That is, and the Z naught has been given to us as a real 50 ohm, because when we refer to a line as a 50 ohm line, all we are saying that its characteristic impedance is 50 ohms. So all the information you need is here. The only thing now this question would be testing is whether you understand what do we mean by distortionless line, and what do we mean by capacitance per unit length, and so forth. So for a distortionless line, we say that R prime by L prime is equal to G prime by C prime, and therefore we can get the Z naught or the L prime from the value for that equation there, because Z naught is just the root of L prime by C prime, and we know that that is 50 ohms. And therefore, alpha given as 0.01 dB per meter. Remember, if you are given in dB per meter, you have to change that into nepers per meter, and we know that the dB, we have 8.69 dB per meter per dB. Okay, the dB per neper, so to speak. Because all we can do is that if you have a function y equal to the natural log of x, we can therefore write that x is equal to the e raised to y, and therefore we can now start taking the logarithms to base 10, and remember that since we are dealing with power, we must multiply that one by 10 and logarithm of that value, and usually it's 20 log because the alpha may not be given in terms of power, but in terms of voltages and the likes, and therefore we know that power is proportional to current squared or to voltage squared. So that's where you get the 8.69 or 8.686 dB per neper, and you divide now therefore the value of the characteristic impedance, okay, that is the attenuation. We divide that one by the value of the dB per neper, so to speak. So this, I think, is a problem. It should be unity, not 0.8. I think that's an error. So, and thus we can therefore get a value for R prime as alpha multiplied by Z naught, and we get 0.06 ohm per meter. L prime is C prime multiplied by Z naught square from the expression for Z naught, and we get 0.25 microhenries per meter, and the conductance is G prime equal to R prime C prime by L prime. We get about 28.8 microsiemens per meter. So that's the first value obtained. And part B, phase velocity is of course given by 1 over root L prime C prime, and we can get that one given by Z multiplied 2 times 10 raised to 8 meters per second. We could also get it just from the value of the impedance. okay, the characteristic impedance and the capacitance. We don't have to always go to calculate L prime first. Who can tell me how we can get this? Can you express Vp in terms of C prime and Z naught? You have half a minute to do this. So do you have a solution yet?
1 over C prime times Z naught.
Yeah, so you can see you can already get the Vp without actually getting the value of L prime. So this, you have to keep these relationships in mind and how you can get one from the other, because it's the way you will even be approaching your work even in the field. Sometimes you don't have a given piece of information, but you have another one. So try to always see how you can express the required, values from whatever you already have without having to calculate them. So part C, all we are required to do is to get the value of the voltage at the given position Z to the incident voltage, that is voltage amplitude. And we see that that is going to be given by the ratio is going to be given by the attenuation factor, which is the exponent of minus alpha and multiplied by Z. And we need it to be at Z at 1 kilometer. We need to get the value, and we get that one is just going to be given by 31.7%. And at 5 kilometers is going to be down by up to 0.32%, so to speak. Okay. So we note that for a traveling wave on a transmission line, the attenuation constant will be given by alpha equal to the real part of gamma, and we can say that is the real part of that product. It should be the square root, not just the as they appear. So we can always put a square root sign there to get the value for gamma. This is an error. I'll correct that. And this can be obtained from a power relation as well, where we note that the line voltage and the current on an infinitely long transmission line would have a phasor representation with only the positive going wave components, that is Vz is equal to V plus exponent of minus alpha plus j beta z, and I z is equal to V plus by Z naught and multiplied by the exponent of minus alpha plus j beta z. And when we multiply those out, we can say that the time average power that propagated down the line across the plane, okay, at Z is just going to be given by Pz equal to a half the real part of Vz and multiplied by the conjugate, complex conjugate of the current Z. And this is an expression which I've already found in power systems or I think machines and or circuit theory. So this gives us a value of a half the amplitude squared divided by the real part or the modulus of Z naught squared and multiplied by the real part of Z naught and exponent of minus twice alpha z. The reason why we are taking the real part of Z naught is because we recall that as long as we have an attenuation in the line, the Z naught may not be a purely resistive characteristic impedance, but it could be a complex impedance, and therefore you only need the real part of it to get the value for that. If you look at that equation there, it's just all we are saying is that it's I squared multiplied by R, so to speak, and multiplied by the attenuation factor. And from the principle of energy conservation, then we require that the rate of decrease of Pz at a plane Z with distance down the line to be equal to the time average power loss from that line, because the only reason why this power is getting dissipated is just because it's getting leaked into the conductors. And therefore, we can get it as, if we differentiate Pz with respect to Z, we'll get the power loss, and we get something like twice alpha multiplied by Pz, where Pz is, of course, the local average power propagating down the line at that local position. And therefore, alpha can be given as Pm, or the power loss at the plane Z, divided by the local power, average power propagating down the line, and multiplied by 2. So, example 3 then. Find the attenuation constant of a lossy transmission line with R prime, L prime, G prime, and C prime using the power relation that we have just seen, and specialize the results in part A to obtain the attenuation constant for a low loss and a distortionless line. So we have two tasks to do. First of all, we get an expression for the attenuation constant, and then we specialize that expression for two cases where we have low loss, and immediately you are told low loss, all we are saying is that R prime is much smaller than omega L prime, and G prime is much smaller than J omega, or omega C prime, so to speak. Distortionness, remember, is the ratios of the per unit length parameters that we are interested in, which must be equal. So for a lossy transmission line, the time average power loss per unit length is going to be given by that value there, where we are having the I squared Z multiplied by R prime plus V squared Z multiplied by G prime. And this can be taken out, and we get a value of R prime by G squared prime multiplied by Z, the modulus of Z naught squared, and multiplied by the exponent of minus twice alpha Z. And thus, alpha is just going to be given by that value there, which is in nepers per meter. So for a low loss line, the Z naught is approximately the square root of L prime by C prime, and alpha is approximately a half of R prime by Z naught plus G prime by R naught, and we get that is going to be that value there that we have. And for a distortionless line, the Z naught is again given by root L prime by C prime, and the two ratios are equal, and we get that alpha is now going to be R prime divided by the characteristic impedance. So when the lines are rarely infinite. Even the Kenya power lines that we get power from Kindaruma up to Nairobi substation or any other substation, we can never be described as infinite. Because at the frequency at which Kenya Power is transmitting power, that is 50 hertz, can you quickly compute for me the wavelength of such a signal, given that the signal is propagating through air? Assume the signal is propagating as a plane wave. Quickly compute that wavelength.
$6,000 kilometers.
Yeah, 6,000 kilometers. What is the distance from, say, Mombasa to Malaba? No guesses.
Marine 32 kilometers.
It's what?
930 kilometers.
930 kilometers. Compared to the wavelength of the signal, you can see that when a power signal is being generated from Kitevu, it hardly even completes a cycle, okay, to get to Malaba, so to speak. This is what we are talking about, distributed circuits. And therefore, when we say that a circuit is small, we shall be using the electrical lengths rather than the actual lengths of the wires themselves. And the electrical length is the length of the wire in relation to the wavelength of the signal that is propagating on that wire. So a circuit will be big or small depending on the relationship between its dimensions and the wavelength of the wavelength of the signals that are being propagated on it. So we can see that many times the lines, the infinite line is very nice to look at, to work with. It's very easy and joyful because we only have one wave component traveling on it. But rarely that doesn't happen in practice. And therefore, most of the lines that you are going to be dealing with are going to be finite length. And therefore, the general solutions of the Helmholtz equations that will govern the voltage and current waves on a transmission line will generally have the form that the line voltage Vz is going to be given by a positive going wave component plus a negative going wave component, that is V plus exponent of minus gamma z plus V minus exponent of gamma z. And the current is going to be given by Iz equal to I plus exponent of minus gamma z plus I minus exponent of gamma z. Now, gamma it will be in general complex because the lines will rarely be lossless, and both terms of the solutions must be present on that in the solution. We shall see cases where the reflected waves may be omitted because of the special way in which you have terminated the lines. So the characteristic impedance of the line is therefore defined as the ratios of the corresponding wave components alone. That is, we assume only that component of the wave is propagating on that line. Say, for example, we can use the positive going components of the current and the voltage, and we get Z0. And we could take the value of the voltage and the negative Z traveling waves, that is V minus exponent gamma z, and divide that with I minus exponent gamma z, and we'll get a value of Z0. But what we'll see is that the relationship between Vz and Iz is through a differential. That is, it's a derivative, so to speak. And therefore, if we differentiate the voltage waveform, we'll see that it will be related to the current in some given way. Okay? And therefore, we'll see that for the case, for it to be a positive characteristic impedance, then we must multiply by a minus sign when we are dealing with the reflected waves. This is something you can recall also when we were looking at the fields, that is the E fields and the magnetic field intensity H in the last semester. The intrinsic impedance was also being divided by multiplied by minus when we were dealing with the current, so to speak. So the reflected waves, V minus Z exponent of gamma Z and I minus Z exponent of gamma Z will vanish when the line is terminated in its characteristic impedance. That is, we can have a short line, but the load, we arrange that the load that is terminating that line be exactly equal to Z0. If it's exactly equal to Z0, then the wave that is propagating, or the incident wave on the line, will see the line as an infinite line. Okay? So we consider a load ZL that is connected to a sinusoidal generator VG. That is, the VG has a harmonic time dependence with a source impedance ZG, which could be real or complex, through a finite length of line of length L, okay, as shown in that diagram. Now, the length of the line is measured from the reference plane at the incident port to the receiving port there, the port 2, the output port of that line. So it's given as L. What I've done here is that I've rearranged my coordinate system and shifted it to the output port so that the Z increases positive in the to the right, and while it's decreasing or it's becoming increasingly negative as we travel towards the generator. So that ZL is terminating that line there. Remember, because of this reference plane we have done here, this wire that is connecting the ZL to the line is assumed to be of 0 length. That is, this load here is exactly at that point there. But we have just stretched it out for clarity. Okay? Otherwise, if this length had an extra, okay, had a finite length, then would this finite length would change what the load sees or what the wave sees as terminating it. Okay, so this is put out there just to clarify, but the load is exactly at the reference plane there, and therefore the voltage across the load is VL, this being a line voltage, and the current going through the load is IL. These are all in phasor form. The input current at the reference plane to the line is II, and the voltage or the input voltage across the inputs to the line is ZI. And therefore, if you were to look into the line, looking toward the termination, that is ZL, would see an input impedance for that termination as Zi. Our line is described by 2 parameters, that is the characteristic impedance Z0 of the line, as well as the propagation constant gamma, and that is enough to tell us what the line is. That is gamma, Z0, and L describe completely the characteristics of our line. Now, again, for the generator, we must view it as being connected exactly at that point, so that these lines that are connected to the generator are all 0 length lines, so to speak. So for convenience, we assume that the load is at Z equal to 0, so that the source or the generator is seen to be connected at Z equal to minus L. And thus, at the load, we can use the transmission line expressions for the line voltage, that the line voltage at Z equal to 0 is the same as the load voltage, and this must be given by the V plus V minus. That is, in the exponents, if we replace Z by 0, we will get that those exponent will be exponent of 0, and which is unity. And therefore, we just get those values there as V plus V minus. The current at Z equal to 0 is going to be given by the load current IL, and this is given by I plus I minus. And this we can see is just the same as V plus by Z0 minus V minus by Z0, because if we divided V minus by I minus, we'd get minus Z0, and V plus by I plus will get positive Z0, and therefore we can write it this expression as shown. Now, by Ohm's law, that is from circuit theory, we know that the load voltage VL is going to be given by the current through the load multiplied by its impedance. It doesn't matter whether it's a complex impedance or a real impedance, that is a real resistance. And therefore, we can then express the wave amplitudes in terms of the load current by writing that IL multiplied by ZL which is VL, is equal to V plus V minus, and IL multiplied by Z naught is equal to V plus minus V minus. And now we can add these two expressions to get an expression for V plus, and we subtract the two expressions to get a value for V minus. Half a minute to do this. Do we have a solution? Hey, do you have a solution yet?
For V positive,
Yeah.
it's IL into ZL plus Z naught over 2.
Yeah, that's correct. So there we have the expressions. And therefore, we put the line voltage at any value of Z. Now we can use the amplitude that we have computed in there and collect the terms. Now, if we look at the values of IL multiplied by ZL, IL by 2 multiplied by ZL, you can see this one we have an exponent of minus gamma Z, and here we have an exponent of gamma Z. So if we combine those two, we get that is just going to be the hyperbolic cosine of gamma Z. Okay, because it's exponent of minus gamma Z plus exponent of gamma Z. If we look at the expression with the Z naught, we see that the exponent of minus gamma Z is subtracting the exponent of gamma Z. And therefore, that is the negative of the hyperbolic sign of gamma Z. And therefore, we can write the line voltage at Z as given as IL multiplied by the ZL, the hyperbolic cosine of gamma Z, minus IL multiplied by Z naught, the hyperbolic sine of gamma Z. And for the current, we do the same, and we see that now we have a separation. The reason why I haven't cancelled the Z naught here is just so that we can see the expressions as they look in full. And here we just have a similar value, that is IL divided by Z naught and multiplied by Z naught cosine, hyperbolic cosine of gamma Z, minus ZL hyperbolic sine of gamma Z. So if we take the ratios of the line voltage to the current, to the line current at the position Z on the line, we'll get from circuit theory that voltage divided by current is impedance. And therefore, we describe that one as a wave impedance or a voltage wave impedance at the position Z, and we call it a ZZ, which is defined as VZ divided by IZ, which are the line voltages and the line current. And this is equal to Z naught, ZL, hyperbolic cosine gamma Z, minus Z naught, hyperbolic sine gamma Z over Z naught, hyperbolic cosine, and so forth. You can actually try to do that for yourselves. That is, use what we have here for the voltage and for the current, and quickly get that ratio. See whether you get the ratio as I have it. Yeah, it may appear to be looking a little bit boring, having to ask you to do it by hand all this time, but it's because I've noticed that for most of us, we have problems with trying to manipulate expressions, and it's important that we get comfortable with it. So let's get that expression for the impedance. Yeah, that one should take you just a minute, I think. Anyone already convinced themselves that my expression is correct? That's all I want you to do. Has anyone obtained this expression?
Yes, it's correct.
Yes. So usually this expression, therefore, that's thanks. This expression usually is written by taking out the hyperbolic cosine, that is factorizing it out, and therefore you'll get it in many times. It will be given as Z0, ZL minus Z0, hyperbolic tangent of gamma Z over Z0 minus ZL, hyperbolic tangent of gamma Z. This looks very much like what you have already met in transmission lines in third year in ECT. But here, we also obtained similar values when we were looking at waves. And the reason why these values are the same, or the forms look the same, where VZ is replaced by is replacing EZ and IZ is replacing HZ, is because for TEM waves, the wave characteristics are the same. The voltages travel as plane waves, so to speak, just like they were doing in unbounded media. Now, this impedance must be seen as the impedance seen looking toward the load at the plane Z from the load. If we are at any plane Z and we look towards the load, we'll measure a voltage or an impedance, an input impedance given by Z of Z. And hence, when we are at the generator, we can call that the input impedance to the terminated line, terminated in ZL, and we can write that Z equal to minus L, and we get that the input impedance defined as the line voltage as at the input, that is at minus L, over the input current at minus L is going to be given by VI by II, and we get that is going to be given by Z0, the ZL minus that tangent and so forth. And since the tangent is an odd function of the argument, you can see that this comes out as negative hyperbolic tangent of gamma Z, and we get it as Z0, ZL plus Z0, hyperbolic tangent of gamma Z over Z0 plus ZL, hyperbolic tangent of gamma L. And this is the impedance that the generator would be seeing when looking toward that load, that terminating load. Okay. So as far as the generator is concerned, we have the load is connected. Okay. The load that is connected to it has an impedance Zi, regardless of what that line is. And we can reduce, therefore, the termination of the line and the line section itself with a impedance of Zi. And therefore, we see that the line has transformed ZL into another impedance, Zi, seen by the generator. So the line is acting as an impedance transformer, so to speak. So thus, as far as the generator is concerned, the terminated finite length line can be replaced by this impedance Zi as shown below. Now, our transmission line circuit looked very weird because we had lines all over, but now we get a simple circuit theory diagram or equivalent circuit where we just have a generator of open circuit VG and open circuit voltage VG, a source impedance of ZG, a current II will be going through that, driving a load of Zi. Okay, and therefore the current that will be absorbed by the load is going to be II, and the voltage across the load is going to be VI. And the input voltage and current can then be computed as follows, that VI is equal to the potential divider expression, that is Zi over Zi plus Zg multiplied by Vg. And the current is just simply the open circuit voltage of the generator divided by the total impedance that is seen. We can see that the Zi and Zg are in series as far as the generator is concerned. So the time average power that is delivered by that generator at the input terminals of the line is therefore going to be given by Pi average equal to a half the real part of Vi multiplied by the complex conjugate of II. And the delivered average power to the load is given by a half real part of Vn multiplied by the complex conjugate of IL, or the load current, and we get a value of VL by ZL squared and multiplied by RL being the real part of ZL. So if the line were lossless, that is, if gamma was just equal to J beta, then we would expect that the input power, that is the incident power on the line at its input, must be equal to the power absorbed in the load, because the line is lossless. So power in is the same as power out at the end of the line. And if ZL were made equal to Z0, then the impedance seen by the generator at a distance Z is going to be given by Z0. And this we can see it from here. If you are to make ZL equal to Z0, okay, so we replace everywhere by everywhere ZL appears, we replace it by Z0, and we'll see that that expression, this ratio here, is going to be unity, and we just get a value of Z0. Okay, so that's what I meant about that. And in this case, the line voltage and the current at any Z will be given by Vz is equal to IL Z0 exponent of minus gamma Z, and this is equal to just simply VL exponent of minus gamma Z. And the current is just going to be given by the load current multiplied by the exponent of minus gamma Z. And no reflections then occur on the line, and the line will therefore be described as matched to the load. So on an infinite length, or on a finite length lossless transmission line, okay, terminated in its own characteristic impedance, the voltage and current distribution on the line will be the same as though the line were infinitely long. okay, there would be no reflections or no reflection components on that line. So in this case, the line is said to be matched to the load. Example 4 then. A signal generator with a source resistance of 1 ohm and an open circuit voltage Vg equal to 0.3 cos twice pi multiplied by 10 to the 8 t volts is connected to a 50 ohm lossless transmission line. The line is 4 meters long and the measured velocity of the wave on the line is 2.5 times 10 raised to 8 meters per second. For a matched load, determine the instantaneous voltage and current at an arbitrary location on the line, and B, the expression for the instantaneous voltage and current at the load, and 3, you get the average power transmitted to the load. Now here, the voltage has been given, okay, in terms of the instantaneous values. All we are saying is that it has a phase of 0, doesn't have any phase there, and therefore in terms of phasors, that will just be 0.3 volts. That is Vz or Vg is going to be given by 0.3 volts at 0 degrees. Okay, that's when you are working with the phasors. But this is the time variation as well. One thing we have to see here is that the line is lossless. We have been told it's lossless. Therefore, the characteristic impedance is going to be a real value, and therefore it's 50 ohms for that particular case. We have been given the what we call the length of the line, and we have been told what the characteristic or the phase velocity is going to be, okay, on that line, and therefore we know what the propagation constant is going to be from that velocity. In some cases, the velocity on the line will be given as a velocity factor. The velocity factor is usually the velocity, the phase velocity on the line divided by the phase velocity of light in free space. Okay, that is the Vp on the line divided by C will be given, it will be described as the velocity factor. So once you are given the velocity factor or the absolute velocity on the line, you should always be able to compute the rest. So part A is that we have that the line, the phasor, the generator voltage phasor, open circuit voltage is 0.3 volts, okay, and has a phase angle of 0 degrees. The Zg, which is a real value, and it's 1 ohm. The line voltage, the line characteristic impedance is 50 ohm. We've been given the value of omega is twice pi multiplied by 10 to the 8 radians per second, and the Vp is given there as 2.5 times 10 raised to 8 meters per second, and the length is 4 meters. So when going forward, whenever I give you a task or a problem to solve, the first thing I'll expect you guys to do, or I'll request you guys to be doing, is to try and write down the given information. Write it all down. Oftentimes you'll find some of the information is not required for the task that you have been set, but it's always good to know what you know and what you need to know but has not been given. Okay, so every time you do or you attempt a problem in electrodynamics, first of all, look at the question, write down the given information. Extract out the information that you require. Okay, so we have been told that the line is matched, and therefore we know that the input impedance is just going to be equal to the characteristic impedance of the line, and that is going to be equal to 50 ohms. The voltage and current at the input will therefore be given by what we already found before is Zi over Zi plus Zg and multiply by Vg, and we get a value of 0.294 at 0 degrees phase angle. And the current is 5.9 milliamps, also with 0 phase, because the impedances are all real resistive. They are resistive, all of them. So since only the forward wave exists on that lossless line, we have that gamma is equal to J beta equal to J omega by Vp, but this is not a consequence of the only one forward wave existing, because of the lossless nature of the line. That's why gamma is equal to J beta, and we can always get that value as J 0.8 pi radians per meter. In these calculations, you don't have to always multiply out the pi. Leave the pi there, because most of the times the pi is usually maybe divided by another expression with a pi in it, and it would have been useless to actually multiply it out and then come again and divide it out. So always leave them there until the last minute, okay? And Vz is equal to that value there multiplied by the exponent of minus J 0.8 pi Z. So this is the gamma that we have computed up there, and that's the expression for the forward wave, and the current will be given as that value. And hence, the instantaneous value, just like we did last semester, is that we get the phasor form of the quantity multiplied by exponent of J omega t and extract out the real part. Many times, I'll always use the cosine reference. You can always use the cosine reference function, but there are some of us who are fond of sine, so you can always you can take the imaginary part, if you like, of that product, and then the value will be in sine. But when you compute them out, you'll find that they'll come back to the same kind of expression. So really, you can have it as a sine or a cosine, but it's usually much better for you to use only what we call the cosine reference function. And therefore, the instantaneous variation of the voltage, that is Vz and T, is given as shown there, and the current is also given as shown there. B, at the load, we have Z is equal to L equal to 4 meters, and hence we can just replace the Z with the value of L that we have there, that is 4 meters, and once we multiply through, we get a value of that nature. And C, if you like, you can now put this one across, that is, you can extract this one out using the trigonometric expansions to get only the cosine of omega t, if you like. But this is just a phase that will come out of it. And C, we have that the average power is input power is going to be equal to the average output power, because the line is lossless, and we can get that one as 87 milliwatts. 0.87 milliwatts, so to speak. So we now want to see how can we use our line as a circuit element. We have seen that a section of line terminated in a load impedance can be used as an impedance transformer to transform that impedance ZL into a lumped element impedance ZI that at the input of that line. Now, at ultra high frequencies, that is from about 300 megahertz to 3 gigahertz, any lumped element components, such as these simple resistors you get in the lab, the inductors which have been coiled into a lumped kind of circuit, or capacitors that we get there, such as electrolytic capacitors and the tantalum ones and so forth, will be very, very difficult to fabricate at high frequencies. You can't get pure ones, because these resistors will always have a section of line that is a lead which comes from the lumped circuit itself, or the lumped element or resistance, and then a wire to connect it to the circuit board. And that length of wire will introduce those transmission line characteristics. And therefore, in the end, we'll no longer be seeing a resistor, but you'll see one, because the positive side and the grounded side are at different potentials, there will be a stress capacitance developed between across the resistor. So the first thing we have there is a capacitance shunting that resistor. Two, the line itself, the section of line that you have, the lead, the current flowing through it will develop a magnetic field around the line, and that magnetic field can be per unit current is an inductance. Again, we see that the resistor now will have an inductor in series with the resistor, and the whole mess is then shunted by a capacitor, and therefore at high frequency, a simple resistor that we had a 1 kilo ohm resistor now starts looking like a network, an RLC network, and at some given frequency, the network will resonate, okay, and we'll see that we have an impedance that is very different from what we started with. Capacitors are the same, and inductors are the same, because between the coils of the inductance, there will always be a coupling capacitors between the coils, because they are different potentials. The coils themselves have finite conductivity, and therefore you have to add in a resistance to the coil. And in the end, we find that all these lumped elements, element components that we use happily in circuit theory no longer apply at high frequencies. So we can, however, use sections of transmission lines to simulate certain lumped element functions. One, we can simulate capacitance and inductance. And two, we could use it to match any terminating nodes to the source impedance of the generator, or when we are seeking maximum power transfer. From circuit theory, we saw that the power transferred will be maximum if the load is equal to the complex conjugate of the load is equal to the source impedance, and therefore source impedance, and therefore we get maximum power transfer conditions from circuit theory. So for most practical cases, short sections of line with a length of L much smaller than the wavelength of the signal can be considered to be lossless, because then gamma L will be, the alpha multiplied by L will be very, very small, and therefore the losses, the wave will not have attenuated much if L is small. And therefore gamma L will therefore be written as an approximate J beta and multiplied by L. And Z0, that is the characteristic impedance of such a line, is therefore going to be purely resistive, and we can write that the hyperbolic tangent of gamma L will be approximately J multiplied by the tangent of beta L, okay, because we have replaced gamma by that. And we can see that the tangent, if beta L is much smaller than unity, we can always say that the J tan beta L is just going to be given by J beta L, so to speak. But for now, let's just keep that one as it is. And hence, the impedance that we computed Zi seen looking into the input of the line section and looking toward the load, then becomes Zi equal to Z0, ZL plus J Z0 tan beta L over Z0 plus J ZL tan beta L. This is an expression that I think you are familiar with. Now, if ZL is equal to infinity, that is, we open circuited that section of line, we would get then an input impedance for an open circuited section of line as minus J Z0 divided by the tangent of beta L. This can be seen from this expression here. ZL is infinity, therefore this can be ignored in relation to ZL, And here, Z0 can be ignored in relation to the JZL tangent of beta L. And that's why we have this expression here that is going to be approximately minus J Z0 by tan beta L. And we can write it as the minus of J Z0 and the hyperbolic and the cotangent of beta L. And thus, depending on the sign that the cotangent of beta L has, because we know that the cotangent of beta L will be positive or negative depending on the argument beta L, where beta L is called the electrical length of that line section, and it will be measured in angle, in radians or in degrees, then we can write it that Zi open circuit can have either an inductive or a capacitive characteristic. That is, if cot beta L is positive, then that line section will behave as a capacitive reactance. If cot beta L is negative, the line section will behave as an inductive reactance. So if beta L is as well much smaller than unity, then the tangent of beta L is approximately equal to beta L in radians, not in degrees, but in radians, and Zi open circuit will therefore be approximately Z0 over J beta L, and we can see that this, if we replace the value of beta L by its value, that is omega root L prime C prime, and multiplied by the L, and we have the characteristic impedance as root L prime by C prime, we get that that is going to be given by 1 over J omega C prime multiplied by L. Remember, C prime was a capacitance of the line per unit length. We multiply it by the length of the section of line, and therefore C prime L is equal to a capacitor. And we see that Zi open circuit for that line is going to be a capacitive impedance or the impedance of a capacitor of value C prime multiplied by L. In practice, we can only make ZL to be large when we open circuit the line section, just like what we have said about the lumped element components. When the two conductors of the open circuit are at different potentials, and therefore as the frequency increases, the stray capacitance between the two lines, the two conductors, becomes important. And therefore, in practice, we can only have a very high open circuit, but that open circuit will not be infinite. It won't have an infinite impedance because of those stray capacitances. Another thing that would get is that an open circuited line will behave because the field lines are trying to attach on, okay, they leave the one conductor and terminate at the other conductor at normal incidence. That is, then who is that with the, please mute your microphone, please. So the line, the field lines or the electric field lines must always be normal to the conductor surfaces if the conductor surfaces are perfectly conducting, and therefore as we get nearer the end of the line, the lines will start to bulge out. That's what we call the fringing effects. And that fringing effect in the end is that the lines will detach and they now be radiated as a radiation field. And that represents losses. So even if the line was lossless, it will now start having loss because power is being radiated away from the load itself. So another thing is, of course, what I've just said, that the capacitance, the stress capacitance will force that thing. And therefore, and another thing we have to show is that mechanical strength of the line is also compromised because leaving, say for example, if we have an air line where the conductors are just separated by air, it will be very difficult for us to maintain the separation of the conductors constant. So Strictly speaking, I'm sure you have seen this kind of diagrams before when you are dealing with Foster lines and core lines when you are making filters. So the variation of the input impedance of an open circuit short line section with the line length, it will be illustrated as shown. If the line is quarter lambda, we see that the input impedance will be seen as 0, okay? So if it's a half, it will go positive, and then we have those things. Just like the tangent or the cotangent kind of expression that we have up there. Now, if ZL is equal to 0, that is, we short circuit that line at the output end, then we see that we replace ZL by 0 everywhere, and our expression for ZI for that short circuited condition will just be J Z0 tangent of beta L. And this, depending on the sign of tan beta L, can either be a capacitance or an inductance. So for very short lines, just like we saw, is so that the tan beta L can be approximated by beta L, and therefore this ZI short circuit just going to be given by J Z0 beta L, and we replace those ones by the appropriate expressions for those expressions, and we see it's going to be an inductive impedance. L prime, which is inductance per unit length, and L being the length of the line, then gives the L prime multiplied by L as an effective inductance. Okay? So the input reactances of open or short-circuited transmission lines will just be the same if their lengths differ by a factor 2n plus 1 or an odd multiple of lambda by 4, where n is equal to 0, 1, 2, 3, and so forth. And that's the beauty of representing the inductance and capacitance, especially when you're building a filter where you need an inductance and a capacitor. If you are to build that filter using transmission line elements, then what you'll have is that at given frequencies, we'll have the condition, the resonance condition appearing in that filter. So the variation of the input impedance for the short-circuited line is therefore shown as shown there, and we see is the negative of what we had for the open-circuited sectional line. And if L is such that L is an odd multiple of lambda by 4, we see the following. You can see that beta L is just going to be given by twice n plus 1, or odd multiple of pi by 2, and tan beta L will therefore be given by the plus or minus infinity, because we know that the tangent of 90 degrees is infinite. And therefore, since this can be 270 or 90 degrees or y and so forth, then plus or minus 90 degrees, we can always get that being a plus or minus infinity. And in this case, all we can see is that Zi is going to be given by Z0 squared divided by ZL. Here I'm using R0 to represent a real Z0, but I think I should change this to Z0 so that we don't have too many variables in our notes. So we see that a section of line that is quarter lambda long will have an input impedance that is the characteristic of the impedance of the line square divided by the line termination. So for L equal to n lambda by 2, that is integer multiples lambda by 2, then we see that beta L is just going to be given by n pi, and therefore the tangent is going to be equal to 0. And we see that Zi will exactly be equal to ZL. That is, the line is transparent, okay? As far as the generator is concerned, as long as the line length is lambda by 2 or an integer thereof, multiple thereof, it will always see the load as it is. That is, there's no transformation of that load. The other time there's a transformation of the load. So what we can say is the following. For this particular case of lambda by 4, if the line is terminated in a short circuit, the impedance that generator will see will be an open circuit. It will see an open, it will assume that it's terminated in an open circuit. Okay. Now, if you are to make the ZL an open circuit, the generator will see a short circuit. And this is very important, especially when you are designing high frequency circuits or systems, because at certain frequencies, depending on how far your load is from the generator, at certain frequencies, if you use long lines, what would happen is that the signal will be short-circuited and you don't know why, or it would be open-circuited and you don't know why as well. Especially for those of us who want to use a single music amplifier in the house, and then we run a very long line to connect our 4 ohm speakers to the amplifier. There are certain frequencies for which the amplifier will be seeing no load, that is open-circuited. The speaker does not appear, or 2, the speaker is short-circuited. And for those frequencies, those ones will be shorted out. It's more like a filter, so to speak. So we can determine, in the lab, we can determine the characteristic impedance and the propagation constant of a given line just by measuring the input impedance of a section of that line with open and short circuit terminations. And we note that for ZL approaching infinity, the ZIOC is equal to Z0, the hyperbolic cotangent of gamma L. For Z0 equal to 0, that is short circuit, the ZI short circuit is going to be equal to Z0, the hyperbolic tangent of gamma L. Here we are not using any approximations. We are using the exact solutions of our input impedances. And therefore, if we multiplied ZL, ZIOC, and ZI short circuit, we see that it's just going to be equal to Z0 squared. And therefore, since we are measuring ZIOC and we measure ZISC, then we just take the square root of the product and we know what the characteristic impedance of that line is going to be. 2, to get the gamma, all we need to do is to divide the 2 values, okay? And once we divide the 2 values, we'll get the following value here. That we are going to get gamma equal to 1 divided by the length of the section of line and the arc hyperbolic tangent of the ratio of ZI, okay, I short-circuited line over the impedance of the open-circuited line. And we take the square root thereof. So we'll get this one in real and imaginary parts as well. So we can get the attenuation constant, and we can also get the phase propagation constant. The problem, though, the errors that we'll get in here is in determining L, okay, and determining the errors we obtain in the measurement of that, okay. So these expressions therefore hold regardless of whether our line is lossy or is not. And therefore I give this example. We say the following: the open and short circuit impedances measured at the input terminals of a lossless transmission line of length 1.5 meters, which is less than quarter lambda on that line, are minus J 54.6 ohms and 1 J 103 ohms respectively. Determine Z0 and gamma of the line, and without changing the operating frequency, that is the frequency you use for the measurement, therefore the lambda by 4, determine the input impedance of a short-circuited section of that line that will be twice as long as the one that we used to determine Z0 and gamma L, and see how long should the short-circuited line be in order that it appears as an open circuit at the input terminals or at that frequency. That is the frequency of operation, our measurement signal. So the Z naught, of course, we have seen is going to be the square root of the product of the ZIOC multiplied by ZISC, and we see that that comes to a value of 75 ohms. And gamma is given as the 1 by L, the hyperbolic arctangent of the ratio ZISC over ZIOC. By pi there to get it in terms of multiples of pi, and we'll see that is about 0.2 pi, I think, radians per meter. B, the gamma multiplied by L is, of course, we multiply that one by its value and we get the total value, and then we can get from the value of ZIOC, we can get that as 75 ohms multiplied by the hyperbolic tangent of J 1.884, which are computed there, and we get a value of minus J 231 ohms. And therefore, we can see that 1.5 meter, we were told is less than lambda by 4, and you can see that that is going to be lambda by twice. Yeah, that is going to be smaller than twice the value, that is the 3 meters, so to speak. For part C, when the line is short-circuited to appear as an open circuit, it has to have an odd multiple of lambda by 4. That is, it should be at least lambda by 4 log, or an odd multiple of lambda by 4 log. Okay, so we have that lambda is going to be given by twice pi by beta, and we get that one as 10 meters. And therefore, for us to get the value of L for it to appear as an open circuit, it will be lambda by 4 plus the n minus 1 multiplied by lambda by 4, and you can get that one as 2.5 plus 5 into n minus 1, and so forth. Okay, so we can always put this one in terms of the lambda by 4 outside by just factorizing out the 2.5 out. We get 1 plus 2 n into whatever, and we get a value of minus or n plus. So with that, I'll give you a 5-minute break. We meet at 5 minutes, but that is at 20 minutes to pass the hour. For you to absorb that, you can use the time to do a bit of stretching, as I'm going to do right now, because we've been sitting for about for more than an hour. It's good to keep our health intact. So you can be enjoying a bit of the music as I go stretch myself a little bit. So we continue from where we left. And we see that when a line is lossy and terminated by short circuit, the input impedance that will be seen will not vanish when L is equal to an integer multiple of lambda by 2. We said that if the line section is lambda by 2 or a multiple, integer multiple thereof long, the input impedance is exactly the same as the termination, the load termination. And therefore, if ZL is equal to 0, we would expect that the input impedance will also be Z equal to 0 as well. Zi is equal to 0. But if the line is lossy, that will not happen. There will be a residual value of impedance that will remain on that line. So we can see that in this case, the short circuit input impedance, that is the impedance of the line, of the short-circuited line, is just going to be given by Z0, the hyperbolic tangent of gamma L, and this can be written in terms of the sine and hyperbolic sine and hyperbolic cosine as a ratio. And what we get is that when we express that one out, that is, we expand the hyperbolic tangent, we get a value of that is shown there, okay? That is hyperbolic sine of alpha L cos beta L plus j sine beta L hyperbolic cosine of alpha L and divided by the same, so to speak. So for L equal to n lambda by 2, we see that the electrical length beta L is just going to be given by n pi radians. And therefore, for all values of n, the sine beta L is going to be 0. And we can see that the open circuit, the short-circuited line input impedance is just going to be given by the Z0 hyperbolic tangent of alpha L, because the cos beta L will cancel out. And if alpha L is much smaller than unity, we can always approximate the hyperbolic tangent by the value of alpha L. And we get that Z0 is therefore going to be given by Z0 alpha L. And since for small alpha L, the tangent alpha L is approximately alpha L. Now, if you look at that kind of expression, since Z0 is almost a pure resistance, we see that we have resonance, a resonance condition. Okay? And this is a series resonance condition, because for a series resonant circuit, RLC circuit, the resonant, the impedance at resonance is usually a minimum. If we didn't have a resistance R in that circuit, then the resonance impedance is just going to be given by 0. It will be going to be 0 ohms. And therefore, since alpha L is small, we can see that this is a condition of a series resonance circuit, okay? Because then that is a minimum kind of impedance that we'll be getting in that case for lines that are n lambda by 2 long. Similarly, if the length of the line was an odd multiple of quarter lambda, again we'll see that when we short circuit that line, we would expect that the input impedance will be infinite. But since the line is lossy, then it will not be infinite, but it will be a given finite value. Okay, large but a finite value. And if we look at that, if we replace L with an n lambda by 4, where n is odd, okay, then cos beta L is going to be always equal to 0. And the short-circuited line input impedance will be given by that value, that is Z0 sine beta L cos a hyperbolic cosine of alpha L over sine hyperbolic sine of alpha L multiplied by sine beta L. And when we do that, we'll get that Z0 will be approximately given by Z0 divided by alpha L when alpha L is small. And since that Z0 by alpha L is going to be a large value, then that appears to be the input impedance or at resonance of a parallel resonance circuit. That is a parallel RLC circuit that we would get, which you call in circuit theory the tank circuit. So the quality factor of the circuit, that is the Q of the circuit, is usually determined by first determining its half power bandwidth. Now, suppose we operate the circuit at a frequency f given by a center frequency f0 offset by a value delta f divided by 2, where delta f is going to be assumed to be much smaller than f0, okay, the center frequency, okay, a shift from the resonance frequency. And therefore, beta L can be expressed as twice pi f divided by the phase velocity and multiplied by L. And we can write that one as twice pi f0 over Vp into 1 plus delta f over twice f0, okay, and multiplied by L. This can therefore be expressed as, since twice pi f0 over Vp is n pi by 2, then we can get that as given as shown there as n pi over 2 plus n pi over 2 into delta f by twice f0, as long as n is odd, that is, and n is equal to n lambda by 4. So the cosine of beta L is therefore going to be given by the cosine of this equation here. And when we expand that equation into the sine and into the trigonometric expansion, we'll get this one is going to be the sine of n pi by 2 sine of that value there. And we'll get the following equation, that it's going to be the minus of sine n pi by 2 delta f over f0, okay, and multiplied by, that is not multiplied, that is that angle. And we can always approximate that one as long as delta f is much smaller than f0, then this expression here is going to be a very small value, and we can approximate it as minus n pi by 2 delta f over twice f, not there. I think there's a problem here. This twice, it should not be there. Yeah, it's the twice f0 that is missing in this particular expression. And therefore, the sine beta L is going to be given by the sine of that And when we expand that, we'll get the cosine of n pi by 2 delta f by twice f naught. And this being a small value, it's the same as getting the cosine of a very small angle, which is very close to unity, because cos 0 is unity. And therefore, this impedance, the input impedance of the short-circuited line will be given by Z0 into alpha L plus J n pi by 2 delta F by 2 F naught, and we are dividing it by. And we can see that we can always get the modulus of that as the characteristic impedance modulus squared divided by the square of the modulus of alpha L plus J n pi by 2 delta F by 2 F naught there. So the magnitude of the input impedance at resonance is then going to be given by Zi short circuit at F naught squared. We are going to replace F by F naught everywhere, and we get a value. We can see that this is going to be given by the maximum. It's going to be the maximum value, and that maximum value is the modulus of Z0 divided by alpha N all squared. This is the parallel circuit we were talking about. And hence, the magnitude of that input impedance can be normalized to its resonance value, and we get a value of 1 over 1 plus n pi by twice alpha L squared delta F by twice F naught whole squared. And therefore, the half power frequency F1 and F2, where F2 is greater than F1, at which that ratio is a half of what it would be at resonance, would be given by that expression there, okay, for n equal to ohm. And therefore, the Q of the parallel resonance circuit is going to be given by F naught, that is the center frequency, divided by the difference between F1 and F2, which is called the bandwidth of the resonance circuit. And we see that that is going to be twice beta divided by twice alpha. So that's the Q of that resonance circuit. So when we assume low loss, then alpha is also low, and therefore the Q is going to be given by omega L prime over R prime plus G prime L prime by C prime. And this is just going to be given by R prime by omega L prime plus G prime over omega C prime. And for a well-insulated line, we can expect that the product G prime L prime by C prime would be much smaller than the resistance of the conduction, the series resistance per unit length, because all we are saying, well-insulated line means that our dielectric, or the dielectric between the conductors, is very close to a perfect dielectric, with therefore G very, very small. And therefore we can make that as that approximation. And in that case, the Q of the circuit becomes omega L prime by R prime, just like we have found in circuit theory. So example 6. The measured attenuation of an air dielectric coaxial line. When you see such a word like air, it can be called an air line or an air coaxial line. Okay, that all it means is that the dielectric between the conductors is actually air. For a coaxial line, of course, for those of us who are keen, we will start wondering, how do we make sure that the center conductor remains, the separation between the outer and inner conductors of the coaxial line remain constant throughout the line, okay? And because we just have air between them. So what, in practice, what we've done is that we'll, at given intervals of the line, we'll put very thin discs of dielectric, okay, to anchor. It's more like we're putting anchors or pillars along the line to try and make sure that the line does not, or the line separation does not change. Okay, if the discs are thin enough, then the dielectric constant of the effective dielectric constant will be that of air, so to speak. So the line is being operated at 400 megahertz, and the attenuation that is measured is 0.01 dB per meter. So we are required to determine the Q and the half power bandwidth of a quarter wavelength section of that line that is terminated in a short circuit. So at f equal to 4 times 10 raised to 8 hertz, that is 400 megahertz, the lambda that we would get for a near line is going to be 0.75 meters, okay? And beta is going to be given by 8.38 radians per meter. The alpha in nepers per meter is going to be given as 0.01 divided by the 8.686 dB per neper, and we get a value, okay, there. And the Q is therefore going to be given by beta by twice alpha, and this is going to be given by 8.38 times 8.69 over 2 times 0.01. That's why I didn't complete the value expression for alpha, and we get a value of 3641. Okay, that is dimensionless because it's a ratio, and delta F is going to be given by F naught over Q, which is equal to 0.11 megahertz. Usually, the bandwidth of a given circuit would be given in terms of fractional bandwidth. By definition, in our courses or in electrodynamics and telecoms, the fractional bandwidth is usually the bandwidth of the circuit divided by the operating center frequency, which is F naught. So delta F by F naught will give us a value of the fractional bandwidth of that circuit. So we can quickly try to get the fractional bandwidth of this circuit. What would it be? You have a minute or half a minute to do that because it's just a division. Could you get the fractional bandwidth of that circuit? Do you have a value?
.75 times 10 to the negative 4.
Yeah, it can also be given as a percentage. You can multiply it by 100. So where do you think this circuit would be useful in practice? Where do you need high Q? This now is borrowing from the lessons you went through in analog electronics. Did you make oscillators? Did you study oscillators?
Yes.
It can be used as a resonator for an oscillator. 2, when you are making, say, something like a notch filter that filters at a single frequency, what you want is that you want to reduce, to make the bandwidth as narrow as possible, and therefore this circuit would be very possible to get that. Now, to get such a high Q at that frequency, just get the value of the resistance that an inductance, that the inductance you would use to get that kind of high Q. Okay, assume you have an inductance of say 10 micro or 1 microhenry, 1 microhenry. Okay, and to get that value of resistance, what that value of Q, what the resistance would have to be.
Could you repeat the question kindly?
I'm asking you to get an inductor, the resistance of an inductor that would give us the same kind of Q. If we were to implement that one, that circuit in terms of, or the resonator in terms of lumped elements, you can assume that L prime and R primes now stand for the lumped element resistance and inductance. So you get the value of the inductor. The inductors have given as 1 microhenry. So you want to get the value of R for that inductor, for you to get the same value of Q of 3641.
Um, 0.11 ohms per meter.
It's not per meter. We have just said you just use it as a, you just use it as a lumped element. That is the resistance. Why did you get 0.11 or 1.11 or whatever it is you said? How is the Q determined or defined?
I used omega L over R.
Over R, yes. So the R is going to be given by omega L divided by 3641. And omega is twice pi multiplied by 400 megahertz multiplied by 1 micro. So it's about 2 pi multiplied by 400 divided by 3641. And therefore you should get something like 0.69, won't you? Ohms. Correct?
Yes.
Yeah, that's the one. So usually such an inductor will be very difficult to make anyway, because most times the resistance, the wire that you'll be using to get a 1 microhenry at that frequency, you may have a few lengths of wire of a given diameter, and you'll get most likely such kind of inductors will have a coil resistance of about 10 ohms. Okay, so it's very difficult to make such a thing, and you can see we can make a high Q just by using a transmission line. So now we want to see how the line would behave if we terminated in a resistive load. Now we are not using a complex load ZL, we are going to use a resistive load RL. And therefore we recall that the line voltage at Z is going to be given by VZ into that expression there, where we are using the complete expression that we had before, rather than using the cosine and hyperbolic cosine and hyperbolic sines. We are not making any assumptions about the lines. That's why we are giving it the propagation constant as gamma rather than beta, J beta. And therefore, when we have such a case, we'll see that the line voltage can be expressed in this form, where we have taken out the positive going term out of the expression and factorized it out. And we have defined ZL minus Z0 over ZL plus Z0 as a value or a factor gamma, and this is multiplying the exponent of twice gamma Z. Okay? So gamma given by ZL minus Z0 by ZL plus Z0 can be written in terms of a modulus, or the absolute value of it multiplied by its phase angle. So it's a phasor kind of quantity. And usually this is defined as the voltage reflection coefficient at the load. We could put a 0 here to show that we are measuring gamma at Z equal to 0, which we define as at the load, but we leave it as it is there. Now, similarly, For the current wave, we could also write it as shown, and we see that the expression is the same as 1 minus gamma exponent of twice gamma z, and multiplying that value there. And we note that the current reflection coefficient may be defined as I minus over I plus, which is the minus of V minus by V plus, that is the negative of the voltage reflection coefficient. So at Z from the load, we can therefore write that Vz is going to be given by that expression, and Iz is going to be given by that expression. And if we divide through, if the line is lossless, gamma is going to be given by J beta, hence Vz is going to be given by that expression there. And we see that the values are just changing to that level. So this should not be I or, it should be I0 to correct that. So the current and voltage phasors will then be obtained as Vz equal to VL, the cosine of beta z minus JIL multiplied by Z0 sine beta z, and Iz equal to IL cos beta z minus J VL by Z0 sine beta L. This we can always obtain from the original expression we had for Vz, which we said was going to be IL ZL multiplied by the hyperbolic cosine of gamma z, and we take the value of gamma as J beta. We'll just get these expressions there. And VL is given, of course, as IL multiplied by ZL. So if ZL is equal to a resistance RL, then we can see that the magnitude, okay, the absolute value of Vz phasor is just going to be given by the VL, the square root of cosine squared plus that value squared. We're just taking these values here. And for the current, it's going to be given by the same value there. And this therefore represent, if we look at this, even if we were to multiply this one by the exponent of J beta L, J omega L, omega T, what we'll get is that this will form a wave that is stationary in space over that line. That is, at a given Z, the Vz will be oscillating up about that level as time varies, but it will not be moving. That is, the constant phase points will not be moving along the line. They'll be stationary. And therefore, they'll have minima and maxima that will be located at fixed planes along that line. So the voltage standing wave ratio, or VSWR, is usually defined as S equal to the maximum value of the voltage divided by the minimum value of that voltage. It doesn't matter, they won't occur at the same point on the line, but we'll have an absolute value of the minimum voltage and an absolute value of the maximum voltage. And this can be given by 1 plus the modulus of gamma over 1 minus the modulus of the gamma there. Okay, from the expression that we have seen here. Okay, where is that value? I think we have it here. From this expression here, we can see that what actually determines the value of that will be this expression here. Okay, and we expect that the maximum value of Vz is going to be the case when that twice J2 beta Z is equal to 0, it is equal to twice pi, okay, or multiples of twice pi. That is 0, twice pi, 4 pi, and so forth. This one will have a value of unity, okay? And this one, if we were to put it as at the value of 0, we'll get that this one will be negative, and therefore this will give us a minimum value. For us to have this one as minimum, then this one must be a multiple of pi, okay? So that this has a negative one, and therefore we'll see it's at subtraction. I'll show how this one comes with the magnitudes, because we can always replace gamma by its expression that we have here, that we defined here, as the absolute value of gamma, and therefore add this value into this equation here, okay? That is J theta gamma into that expression, and therefore it's that expression, whether it's a multiple of twice pi or a multiple of pi, will give us the values for minimum and maximum value of these modulus. And therefore we can note that Vmax, the absolute value of Vmax and absolute value of I mean will occur at the same point of Z equal to the minus Z big M, where the theta gamma minus twice beta Zm is equal to the negative of twice n pi. The reason I'm using the negative value here is because I'll be measuring in the backward direction rather than in the forward direction. That's how we have defined our Z on the line, because the load is measured at the termination. The Z is measured positive from the termination going away from the line. And V minimum and I max will occur also together at a value of Z, or a plane Z, equal to the minus Z small m. And in this case, gamma theta is just going to be an odd multiple of pi. And therefore, we look at the following example. The standing wave ratio on a transmission line is an easily measured quantity. That's just information you have given. It doesn't have, it's only for value to you to know that we can easily measure standing wave ratios. And I don't know whether you have measured this in the lab, or use what we call a slot line. I'm sure in the telecom labs you'll be able to measure the standing wave ratios on a line. So what we are required to do is to show how the value of the terminating resistance on a lossless line of known characteristic impedance and not can be determined by just measuring the voltage standing wave ratio. And B, what is the impedance of the line looking towards the load at a distance gamma lambda by 4, where lambda is the operating wavelength. So how to show this is the following. If there are voltage maxima at Z equal to 0, minus lambda by 2, minus lambda and so forth, then it only means that RL should be smaller than Z0, because the gamma is going to be negative. Since the termination is gamma L, the theta gamma is going to be 0, and therefore RL minus Z0 must be negative for it to have a negative value. If RL is greater than Z0, then gamma L is going to be equal to 0, and Vmax and I mean will occur at beta Z equal to 0, and V mean and I max will occur at Bz equal to the minus pi by 2. And thus, we can write that Vmax is going to be equal to VL, that is at the position of the termination, the voltage is maximum and is equal to the load voltage, and it will be minimum, and the minimum value is going to be given by V0, Z0 by RL multiplied by VL. Okay, where that VL by RL is of course IL, multiplied by the characteristic impedance of the line. And I mean is going to be the same, the value of the current IL, because for RL greater than Z0, we are going towards the infinity or an open circuited line. That is, the load is becoming larger, okay? And therefore the current that will be flowing will be minimum current. And Imax is going to be given by RL divided by Z0 and multiplied by IL. And therefore, when we take the ratios, we'll get the ratios of Vmax by Vmin, which is the same as the absolute value of Imax by Imin, and we get it as going to be equal to S. And this is given as RL over Z0. So if we take that value, then we can see the terminating resistance RL can be obtained from the characteristic impedance of the line and the standing wave ratio that has been measured, and multiplying them together. It will be given as a product of the standing wave ratio by and the characteristic impedance of the line. If RL is smaller than Z0, then RL minus Z naught is going to be negative, and therefore we can say that that one is a value of theta gamma that is minus pi. That is, it's the same as pi, but we use minus pi to represent to keep in touch with our terminology in the measurement of Z. And this must occur at a value at beta Z equal to 0, and therefore Vmax and I mean will occur at beta Z equal to minus pi by 2. So Vmin must be the same. That is, the minimum value of the voltage, of the line voltage, must occur at the termination, and therefore it must be equal to the load voltage, the voltage across the load, and the maximum value will occur a quarter lambda later and will be given as Z naught over RL dL. This you can get from the expressions for the Vz and Iz that we have had there in terms of cosine and sines. And Imax will be IL, that is the maximum value will be of current, will be of the line current, will be the load current, and the minimum value will be given as RL over Z naught IL. And therefore the standing wave ratio is just going to be given by S equal to Z naught by RL, and we see that the load termination resistance is just the characteristic impedance divided by S. So B, lambda is determined from twice the distance between two neighboring voltage or current maxima. So if you look at the standing wave, waves on the line, what we'll see is that we'll have undulating, a voltage that is going sinusoidally with Z. But if you look at the expression for the voltages, the line voltages here, let me show it again. Sorry about this. If you look at these expressions, we have twice beta Z. Okay? Because of this double, then we must notice that this is going to, if you replace this beta by twice pi by lambda, okay, we'll see that that is going to be 4 pi by lambda. And therefore, if we take two adjacent points, okay, it will be representing a lambda that is half the value. Okay, where is that? What did I do? I have a problem with my value here. It has stopped. So the voltage minimum or maximum cannot occur at the, is that the correct value we are talking about? I think I'm going a bit too far. So we say that the lambda will be determined as twice the distance between two neighboring voltage and current maxima or minima. And we can write that as Z equal to minus lambda by 4. Beta Z is going to be given by minus pi by 2. And the cosine of beta Z is going to be 0. And the sine of beta Z is going to be minus 1. And thus, at quarter lambda, we can see that that is going to be given by J I L Z naught. Okay. And I, quarter lambda, is going to be given by J E L by Z. Where here, we are using these expressions here. I'll show these expressions are what we are using. So you put the value of Z equal to minus lambda by 4. If you look at that, if you take Z equal to minus lambda by 4, you'll get that that will go to 0, and that will just remain. and that will go to 0, and that will remain as positive values. So that's what I mean there. And therefore, we can see that Z0, or the Z at minus lambda by 4, is going to be given by Zi, and this is going to be given by the voltage at lambda minus lambda by 4 over I over minus lambda by 4. And you can see that that is going to be given by Z0 squared over Rn, just like we saw for a quarter lambda section of line terminated in a load resistance, load impedance ZL, which in this particular case is equal to a resistance Rn. Now, if the load is arbitrary, by arbitrary we mean it's going to be a complex load rather than resistive, then a voltage minimum or a maximum cannot occur at the termination of the line. Because for this particular case, if the line is lossless or it's lossy, the characteristic impedance is not going to, the voltage reflection coefficient is not going to be a pure value, that is a real value. It's going to be a complex value. It will have a phase. That means that theta gamma cannot be 0, neither can it be just exactly minus pi. It will be some angle in between. So we let ZL be defined as a real part RL plus an imaginary reactance XL. If XL is inductive, of course, that will be plus J. If it's capacitive, it's going to be minus XL. So it really doesn't give us a lot of problems. So this is a general complex load impedance. So if the standing wave is extended, if we were to extend the standing wave beyond the load termination, okay, and a further distance Lm, it's possible for us to reach either a minimum or a maximum of the voltage standing wave amplitude. This is what we have expressed here. So we are saying that if ZL is complex, then on the real line, we have said that here can neither be a maximum or a minimum of the voltage or current. That is the termination point. So we have indicated this by showing that the maximum is just before the termination. And therefore, the value at the termination is different. So all we are saying is that we extend that expression of the standing wave with the dashed line that we have there, and until we reach a minimum point. But if you like, you can also extend it a bit further until you get the maximum point there. So that's what we mean by extending the line. And therefore it means, please mute your microphone, sir or lady. So that is going to be, the termination point is there, and we have added an extra section of line of length Lm to reach a minimum in the voltage waveform. And therefore, we know that between those two minima that we have, the length must be lambda by 2. That is half a lambda, half a wavelength between the two adjacent minimum points. And therefore, we can, since now this one is appearing or is occurring at the termination of our resistance Rm, we are using an Rm that is smaller than Z0 so that we get a minimum value for the voltage at that point. Then we are saying that we now forget about ZL, but use Rm. But when we look into the line, that is the Rm, towards into the line section Lm, towards the Rm terminating, we should be able to get an input impedance that is exactly equal to the ZL that we are using to terminate the actual line. So that's what this whole thing means. So this will not change the voltage distribution. Yes.
Thank you for the lesson. Yeah, I'm afraid our time is up.
Hello?
Hello? Hello?
Yes.
Oh no, I was informing you that our time, the lesson has come to an end.
Okay, fine. Thanks. So I'll stop there. Please try and look at that diagram properly. Make sure you understand it, because that's also a practical way in which you can be measuring those things. So then I'll therefore stop there. We'll continue from there next week. And if there are no questions, then I'll.
I have a question.
Yes.
On slide 86.
Yes.
When you're expanding the hyperbolic term of gamma L, you had put an L afterwards, and I think it was supposed to cancel out. Maybe you can confirm.
I put what?
When expanding the hyperbolic term of gamma L, the L was still there. So I was thinking that it was supposed to cancel out. You can confirm.
86, you said. This one?
Yes.
Oh, what do you mean is missing? This tangent here. Could you please tell me what the problem is?
The L at the end, there's only supposed to be one in the numerator, not both in the numerator and denominator.
But here I've just changed tangent in terms of the sine and the cosine.
Okay, I understand.
So if now, yes. Usually it's more difficult to deal with this tangent because the tangent itself to expand it up there, because if I replace it at alpha plus whatever, I'll have something tan alpha L, hyperbolic tan alpha L multiplied by J tan beta L, and then divide that one by 1 plus, isn't it?
Yes.
Yeah, that's what happens. So it's much easier for me to use with the sines because I can now just do that one immediately. But if you want in terms of the tangent, we can take out these values out, okay? Or we take out this cosine alpha, hyperbolic cosine alpha L cos beta L out, then divide it through. And then you'll see here it will be tan alpha L plus J tan beta L over 1 plus J tan hyperbolic tan alpha L multiplied by tan beta L multiplied by J, isn't it?
Yes.
It's just the same thing. Thanks.
Okay, thank you.
Okay. So if there are no other further questions, then I'll stop the recording and let's meet next week. I've been asked to share the recordings for the week. I'll try and do so immediately they're available. Okay, have a nice weekend then. And we have guys who keep on trying to get into class when we are finishing. I don't know why.